All right, y'all. Today we're going to be talking about systems of not equations, but actually systems of inequalities. And the big difference between an equation and inequality is, of course, that inequality sign in the middle of them instead of that equal sign. Okay, and when we're considering solving and working with systems of inequalities, they're going to work very similar to equations. But the biggest thing is that our answer is not necessarily going to be a specific point or specific values, but this time it might be an area or a set of points or of values. So when we're trying to solve a system of inequalities, we're going to do the same thing for if we grab just a single inequality. We're going to graph the line, and then once we graph that line with our system, we are going to shade that corresponding area for each line. And then once we shade that corresponding area, our answer is going to be that shaded in area. So instead of a specific point like we've had with our systems of equations so far, where we have specific values for x and y or x, y, and z, our answer is going to actually be a set of numbers. So an area, a region. And to kind of see this in action, let's look at example 1. So we have the graph y is less than 1/2 x plus 1. And just a recap of some things when we are graphing these. This is a linear function, so there's two important pieces of information that I want. I want the slope, and then I want the y-intercept. So the y-intercept is the first thing I'm going to pop on the graph, plus 1. And that slope, 1/2, I'm going to use that to go up 1 and over 2 because we use it like rise over run. And that's going to give me that second point. And once I have those 2 points, I can repeat that pattern all the way across my graph. And likewise in the other direction. And that should give me kind of a rough outline of my graph. Now, before I draw on my line, this is the other special consideration that comes with inequalities, and it's how to actually draw your line and shade your graph in. So depending on my inequality sign is going to tell me two things. If my line is going to be solid or dotted, and if my line is going to be shaded above or shaded below. Okay, so our less than signs, less than or equal to, are going to cause us to shade below. Our greater than signs, greater than or equal to, are going to cause us to shade above. If it's just a less than or a greater than, so not equal to, we're going to use a dotted line for our graph. If it is a equals to, though, which means we want to equal that line, we're going to use that solid line instead. So our inequality here for our graph is a less than sign, so we're going to use a dotted line. And then it is a less than sign once again. So instead of shading above, we're going to shade below. And so all of this area down below my graph is my shaded region. That would be my solution. Okay, so pretty simple. That is just graphing one single inequality. Let's look at another one over here on the right. Okay, so if I want to graph y is greater than or equal to -4x minus 2, same thing. I want to do that y-intercept first, which is -2. Then my slope this time is -4 or -4 over 1. So I'm going to go down by 4 and over by 1. And I can repeat that pattern in both directions. And then it is a greater than or equal to. Greater than or equal to means we are going to shade above with a solid line. So solid line. And then we shade above. And so once again, rather straightforward process when it's all done and said. So we see our first graph over on the left, our second graph over on the right. They each have a distinct area, which is their solution set. So anything in that shaded region is going to be the solution to that inequality. Okay. Now, what we're really upgrading this to today is not just to individual graphed inequalities, but actually a system of inequalities. And that's really our big focus today. So when we're doing a system of inequalities, just like we do for a system of equations, we're going to graph both of those inequalities on the same graph. So just like we did before, y is less than 1/2 x, y-intercept of 1, and then a slope of 1/2. Which, of course, gives me my dotted line again for that less than sign. And then for my second graph, y is greater than or equal to negative 4x minus 2. So same thing. Negative 2 for that y-intercept, down by 4 and over by 1. And then same thing in the other direction. And this one is a greater than or equal to, so it is a solid line. And last but not least, we need to add in those shades. So we're going to shade both of them on the same graph, and we're going to see something kind of interesting occur. So my purple graph, it is less than, so I'm shading below. And my red graph, it is greater than or equal to, so I am shading above. And what we should see occur, which we do here, is we now have this overlapping region where both of my inequalities are actually shaded. And so it's definitely not this non-shaded region that is a solution set. And it's not these two individual ones, while that was a solution set to the red graph in the top right and a solution set to the purple graph in the bottom left. Neither of those are a solution set to my system. My solution set for my system is now this region here in the bottom right. So what area on the graph is the solution set? It's going to be that area where the shading overlaps. And as a follow-up question, is 1, 4 in the solution set? So looking for 1, 4, 1, 1, 2, 3, 4 is up here. So 1, 4 falls in one of the shaded regions, but not in the overlapping shaded region. So it would not be a part of that solution set. Okay, so relatively straightforward. I'm going to let you go ahead and do number 2 on your own. So go ahead and pause the video and go ahead and try number 2, and then we'll talk about example 3 together here in a moment. Okay, so pause the video and go ahead and do example 2. All right, looking at example 2, we have y is less than 2x minus 1 and y is greater than negative x plus 2. Okay, so 2x minus 1, that's going to have a y-intercept of negative 1 and then a slope of 2 over 1. And then it is a less than, so it's dotted and shaded below. And then our second graph, y is greater than negative x plus 2. So a y-intercept of positive 2 and then a slope of negative 1, so down 1 over 1. And then that is a greater than, so dotted line and shaded above. So check, make sure your inequalities look the same as mine, graphed. And then last but not least is 3, negative 2 in the solution set. We can see it graphed right there, and it is almost, but not quite. So it is just outside that solution set area. So it would not be in the solution set. Okay, let's go ahead and talk about number 3. So number 3, we have y minus 3x is less than or equal to 2, and negative y plus x is greater than negative 5. And then, of course, once we finish graphing, we want to answer is 2, 3 in the solution set. So Right off the bat, what we should notice is that these linear equations are not solved for y right now, which means currently we cannot graph these by hand. So if we want to be able to graph these equations, we need to actually solve each of them for y. So taking our first equation, y minus 3x is less than or equal to 2. I need to isolate that y so I can add 3x to both sides. And we get y is less than or equal to 3x plus 2. So a nice and simple equation that I can now use to actually graph. Now for our second graph, our negative y plus x is greater than negative 5. Same thing, I want to isolate that y. This time I'm going to have to do a little bit more though. So moving that x, I can subtract x from both sides. So we get negative y is greater than negative 5. Now we'll switch this around. Negative x minus 5. Or, we'll just keep writing the same thing. So negative x minus 5. Okay, and then we still have that negative in front of y, so we can divide everything by a negative 1. And this is going to have two effects. First of all, it's going to change all of our signs, so y and x plus 5. Secondly, and this only occurs with inequalities, but when you divide or multiply by a negative, it's also going to cause that inequality to switch. So instead of it being a greater than like we started with, it's now going to be a less than sign. Okay, so important thing to note if you ever need to solve in our process of graphing. So from here, we can use our 2. So for our first graph, we have y is less than or equal to 3x plus 2. So plus 2 is our y-intercept. Let's plot that on the graph. And of course, y'all, if you want to pause and do this one on your own, you can. And then our slope of 3, so that's going to be up 3 and over by 1. And then it is a less than or equal to sign, so that's going to be a solid line. And then, of course, it is a line, so add our arrows onto the end. And then let's go ahead and graph our other one. Y is less than x plus 5, so y-intercept of 5. 1, 2, 3, 4, 5. And then 1x, so our slope is 1 over 1. And we can just repeat that pattern to get some more points. And of course, you don't have to do all the points, y'all. Once you kind of have an idea, you can stop so that you can actually fill that graph in. And this one is a less than sign, so it is going to be a dotted line. Okay, so then let's go ahead and add in our shading. So with our shading for our first one, it is less than or equal to, so we are going to shade below. And then for our second one, it is also less than, so we are once again going to shade below. And we actually end up with this fairly large combined shaded region, at least fairly large from what we can see on our graph. And then, of course, last but not least, we want to answer this question: is 2, 3 in the solution set? 1, 2, 1, 2, 3. And we can see that 2, 3 is squarely in our solution set this time. Okay, so really only difference on example 3 from either the other 2 examples we had is that we had to solve those equations for y really quickly before we could actually graph them. So nothing too crazy, nothing too different. Okay, let's kind of look at these from a little bit of a different perspective. Let's look at what Serena and Adam have going on. So we have that system of inequalities below. Y is greater than negative 3x plus 5, and y is less than negative 3x minus 2. And Serena and Adam got the same lines graphed, but they shaded a little bit different. Serena shaded the outside of the two lines, and said that because those inequality areas do not overlap, there's actually no solution to the system of inequalities. And then Adam shaded that region in the middle, which means all that area in the middle would actually be our solution set, just like we've had before, that overlapping area. Okay, and we want to consider who is correct. Well, we can look back at those inequalities. So our first inequality, y is negative 3x plus 5. That's going to be this top equation on both graphs, and we are greater than. So we should be shading above that graph. And then y is less than negative 3x minus 2. That's going to be our lower equation, and it's less than, so we're shading below. So between Serena and Adam, I would definitely say that Serena has the correct solution. And we can see that because she shaded on the outside, which follows what that system of equations. And it's really important to note that, just like Serena noted, if our two shaded regions don't ever actually overlap, which is only going to happen if we have perfectly parallel lines and the shaded areas are going away from each other, then we will have no solution for our system of inequalities, because there's nowhere where they would ever overlap and where we could find points that lie in both shaded regions. Okay, so let's finish up. We're going to do one that's maybe a little bit more challenging, a little bit of an application problem. So the Whistling Baker is a bakery that specializes in cupcakes and muffins. They sell cupcakes for $2 each and muffins for $1.25 each. And the Whistling Baker can bake a total of 8 dozen treats each day and needs to make $100 per day. And we want to write a system of linear inequalities to represent this problem situation, and we want to be sure to define your variables. Hey, so go ahead and pause me. What I want you to do is I want you to start. We're going to kind of do this one in pieces, and I want you to go ahead and write this system of linear inequalities. We've done a little bit of practice with writing equations, writing systems from these application problems. So I want to see if you can write this one on your own, given the information. Big thing, think about not just your variables and what coefficients you're going to put into your variables, but think of what those inequality signs should be for your system. All right, y'all, let's talk about these two equations. So first and foremost, I would recommend labeling and deciding your variables. So I decide x is equal to cupcakes, y is equal to muffins. You, of course, could use C and F if you wanted to. I just think sometimes that can be confusing in the context of graphing. So I like to still use x and y. So if you use C and M instead, I would switch them over to x and y. I think it's going to make it a little bit more simpler, but you do you. And then the first piece of information they give us is that cupcakes are $2 each and muffins are $1.25 each. So it makes sense to say 2 times the number of cupcakes plus $1.25 times the number of muffins. And they have to make $100 per day, at least. I would say if they have to make $100, they're probably not cool if they make less. So definitely has to be greater than. And if they make exactly 100, obviously not a great day, but they're okay with that as well. So saying 2x plus 1.25y has to be greater than or equal to that 100 makes the most sense for our first equation. And the second piece of information they also tell us is that the Whistling Baker can bake a total of 8 dozen treats each day. So that can bake a total. That means it can get up to 8 dozen, but it can't make any more, probably, because of their ingredients or their constraints. So the total number of cupcakes plus the total number of muffins can't exceed that 96. So x plus y has to be less than or equal to 96, makes the most sense. Okay, now our next piece is we want to be able to graph this system, because we want to be able to actually see it graphically and be able to use this information. But just like we had that issue before, currently these are not solved for y. So go ahead and pause the video again, and I want you to solve each of these equations for y. You can take that space over there on the right. Look out for anything, some decimals, some fractions you might have to work with, or even any negatives or anything like that might affect our inequalities. All right, so going over our solved inequalities, y'all. Going with our first one, x plus y is less than or equal to 96. That one's relatively straightforward, just subtracting y from both sides. we get that y has to be less than or equal to negative x plus 96. Our second equation, though, a bit more complicated. First off, we want to get that 2x to the other side. So subtracting 2x from both sides, we get 1.25y is greater than or equal to negative 2x plus 100. Then I want to get that 1.25 to the other side, so I can divide everything by 1.25. Now, I don't know about you, but I don't know how to divide by 1.25. So I can convert everything to fractions. Makes it a little bit easier because remember, dividing by a fraction is the same as multiplying by the reciprocal. So negative 2 over 1 divided by 5 over 4 is the same as negative 2 over 1 times 4 fifths, which would give me negative 8 fifths. And 100 over 1 divided by 5 fourths would be the same as 100 over 1 times 4 fifths, which would be the same as 400 over 5. And then just simplifying from there, negative 8 over 5, that can't be simplified, but 400 divided by 5 does give us that plus 80. Okay, so we have y is less than or equal to negative x plus 96, and y is greater than or equal to negative 8 fifths x plus 80. So we now have two inequalities that we can plot and put onto our graph. So once again, go ahead and pause the video, y'all, and I want you to go ahead and graph this system of two inequalities using our two solved inequalities that we found above. Y is less than or equal to, ooh, that is really thick. Y is less than or equal to negative x plus 96, and y is greater than or equal to negative 8 fifths x plus 80. All right, y'all. So hopefully your graph looks something similar to mine. We should have this first function, our y is greater than or equal to negative 8 fifths x plus 80. We're going through 80. We're going down by 8 and to the right by 5. And then it is greater than or equal to, so it is a solid line. And we are going to shade above, which is that purple shade area. And then our second one, y is less than or equal to negative x plus 96. So up here at 96, and then going down and over by 1, and then we are shading below. And so when we get that, we get this nice region here in the middle, which is going to be that nice middle ground between the maximum number of baked goods that we could make and the minimum amount of money that we have to make. So for part C, we want to identify one possible solution and talk about, is this solution reasonable within the context of the problem situation? So obviously we have this whole region here in the center. So there could be a whole slew of possible solutions that we could pick. We could pick something nice and even. So it looks like 40 and 40 would be fine. So 40 muffins, 40 cupcakes, that's going to fall under our 96 threshold. But then more, it should make us more than $100 based on our graph. We could go really high on one side, so 80 cupcakes and only, let's see, 10 muffins should still make us fall on that 96, but still make us that $100, or vice versa. We could go really high in the muffins, so 85 muffins and make only 5 cupcakes. That's still going to get us to fall in that region there in the center. Now, if I was a baker, you're usually baking in dozens, so you might want to pick something that makes a little bit more sense. So maybe something like 48 and 48, which would fall right here on that line. In fact, in terms of that 96, but remember it's less than or equal to 96. And it should still make us that $100 definitely, because we're maximizing those number of muffins and cupcakes. So that's kind of a wrapper on our system of inequalities, y'all. They can get more advanced. We really explored a system of 2 inequalities. You could do a system of even 3 or 4, but it's the same thing whenever you're doing a system of inequalities. We're always looking for those overlapping regions where all the inequalities are involved. That's going to be that solution set.